Let's go ahead and revisit our special right triangles as well. Here we have a chart that lists some common degree measures to radian conversions. And we're choosing these degree values because they're the ones within our special right triangle. So if you can remember the common radian measure, it's going to save you a lot of time. But if you forget, remember that you can always convert by multiplying by pi over 180 or the reciprocal if you want to get back from radians to degrees. So we can do that simple conversion if we need to. So recall our special right triangles, 30, 60, 90, as well as the 45, 45, 90 right triangle. And we're going to come back to these in a minute when we go and look at this next part here, where often we might be asked to find or given the radian measure of a central angle in a circle and given some information. And so we can always actually take our angle measure in a circle and we can draw our right triangle and look for special relationships within the triangle. So for example, we're given the point 2, 2 here, which is the point where this angle intersects the circle in our coordinate grid. The angle down here starts at the origin, which is 0, 0. Well, if we bring this line straight down and we draw a triangle, we see that we have this right triangle right here. Well, we can think about what it means to plot a point in the coordinate grid and what that's going to mean for the lengths of the sides of our triangle. If we start at the origin, we can go right 2 units, and that gives us this length of this leg here as 2, which is the x coordinate of our point. And then we could go up 2 units as well, which makes this leg 2 units, which gives us the y coordinate of our point. So the horizontal leg is x and the vertical leg is y. Now, seeing that we have 2 legs of equal length, we can think back to our special right triangles. Well, our 45, 45 triangle has legs of equal length, which means that if we have side lengths 2 and 2, we know our hypotenuse is 2 square root of 2, and we also know that both of these angles have to measure 45 degrees. So given the point on a circle that this angle falls on, we're able to calculate the degrees of the angles. We can convert those to radians. It'd be pi over 4. We know the lengths of the sides, and we also know the length of the hypotenuse. So let's go ahead and use that in our next example down here. So we're given a circle with the angle AOB, and they tell us that it is pi over 6 radians. This angle is pi over 6. And so we can convert that into degrees, which is a little bit easier for us, as 30 degrees here. So we know that it also measures 30 degrees, either one. And then what we could do is draw an angle, or a side, coming straight down to form our right triangle. So let's make that diagram a little bit bigger. So we have a right triangle with an angle that measures 30 degrees. Well, given that that angle measures 30 degrees, we know that this angle measures 60 degrees. We have a 30, 60, 90 triangle. So given that information, we can look at our diagram on our 30, 60, 90 and know that this side represents x, kind of our unit. That could be any length. And then the second leg is going to be whatever that unit is times the square root of 3. And our hypotenuse will be 2 times whatever that unit is. Well, they're telling us that point A, located up here, point A, has an x coordinate of 2 square root of 3. And recall that the x coordinate is the distance on the horizontal leg from here to here. The distance from here to here is the x coordinate of our point. And so if the x coordinate is 2 square root of 3, and we compare it to our formula here, 2 square root of 3, we know that x has to equal 2. And so they're asking for the y coordinate. Well, the y coordinate is the distance up from the x-axis to the point, up from the x-axis to the point. So if this leg measures 2 root 3, and the other leg measures 2, we know that the y coordinate has to equal 2. The next thing they want us to find is the radius of the circle. Well, look at the diagram really closely of our triangle. The radius extends from the center of the circle to the edge, And on our triangle, the hypotenuse also extends from the center of the circle to the edge. And so if we find the hypotenuse, we know the radius of the circle. Well, going back to our diagram, 2 times the shortest leg will be our radius. So 2 times 2 equals 4. So the radius of our circle is 4. In this figure, we're given the ordered pair, 1, 1/3. And so if we finish off our triangle, we can think about the x-coordinate is 1. That means the horizontal distance on the bottom is 1. And the vertical distance is the square root of 3. This matches up again with our 30, 60, 90 triangle. Let's make this drawing a little bit bigger. 1 root 3. This matches up with our 30, 60, 90 triangle. We just need to figure out what measure each of these angles are. And they're asking for the measure of this interior angle, AOB, and they say it's pi over A. So they want the measure of the angle in radians. So let's first think about what the measure of the angle is going to be in degrees. Well, let's look at the side lengths in relationship to this angle. If I look at my side lengths, I see that opposite this angle is the side square root of 3, and adjacent to it is the side length 1. So let's look at our diagram. Well, what angle has the square root of 3 as the opposite and the 1 as the adjacent? That's going to be our 60-degree angle. Opposite 60 degrees is square root of 3, and adjacent to it is the 1. So we know that this angle down here has to be 60 degrees. Well, if it's 60 degrees, we can do a quick conversion into radians. Multiplying by pi over 180, 60 pi over 180 reduces to pi over 3. So if we want the value of A, and our angle is a measure of pi over A, we know that A equals 3. Now we didn't need it for this question, but we could also fill in the rest of our triangle. We know that this has to be an angle measure of 30 degrees. And then following our formula where the hypotenuse is 2 times the shorter leg, 2 times 1 equals a hypotenuse of